I'm starting on the one that is not the 4-step problem. And we're going to go ahead and start filling this out. It's easier to just kind of jump straight into it and then slow down as I need to as we go through the problem itself. So this is called, it looks like CHI, but it's called chi squared. And the symbol for chi is kind of like an X. So like this one's straight and that one's crooked is your symbol for, like that's what the chi is. And it's chi squared, so it's chi squared. So most of the time, like I have it written out like in words on some stuff, but writing this is fun. So it is a test of independence. And this won't make that much sense right now, but it will eventually, as far as like why I'm making a big deal about this. But the big difference between today and tomorrow is how I get my information. It's going to look the exact same. So it could be like a group of people I have, they're either male or female, and they're either juniors or seniors. And I can have this exact same chart, but it could be two separate things. Well, technically three, but we're not talking about third right now. It depends on how I get my information. So did I specifically set out and make sure that I got a random sample of female and a random sample of male and then figured out which ones are juniors and seniors? Or did I take a random sample of people and record two things, both the gender and the grade level? So for chi-square test of independence, this is what you're writing on the notes. We take one sample, which could technically be the entire population. But the big thing is we take one group. I randomly select one group, and then I record two variables for each individual. So this would be, I just set out and randomly select 100 students. I happen to ask them two questions. Number one, gender. Number two, grade level. So our whole idea here is we're testing of independence. So we're trying to see if they're independent or not. So this is going to be one of the variables and the other variable. So to try to make it less confusing, I'm going to write it as the column variable and the row variable, but that doesn't mean they have to be in that order. It's just kind of confusing if you just write variable and variable. So the way I had it here, one of our variables was gender and one of our variables is grade level. It doesn't really matter if you say the grade level and gender variables are, or the, whichever opposite way I said it, grade level and genders or grade level. It doesn't really matter about that part. So then here they are independent and here they are not. Out of habit, I usually, when I actually do these, write not in capital just so that I'm kind of showing which one I'm saying is which. I'm not going to obviously grade off if you don't do it in capital. But then the same thing's going to be down here. So it's either that they are independent, which is the null hypothesis, or they are not independent, which is the alternative. And this bottom part right here is just saying what we set up there. We have a two-way table from one specific sample. We happen to ask each individual in our sample two different things. So the only thing that's going to end up changing tomorrow is like I specifically set out and get a certain number of females randomly selected and then a certain number of males randomly selected and then only ask them one question each, which seems very similar to what we're doing today. All right, conditions. I'm going to go through this kind of quick. When we usually have 3 conditions, what's our first one? Random. What's our second condition usually, but it's not today? Normal. What's our third condition? When we check normal for proportions, how do we check normal for proportions? Some type of n times p, and we make sure that both the number of successes and the number of failures are what? Greater than or equal to 10. Well, now we might have a two-way table with like 5 by 6 or 2 by 3 or something, and we're going to have a whole bunch of them. So instead of making sure that all of our options or all of our possibles, like success and failure, are at least 10, it's at least 5, but it's still that same concept. But we call it large sample size, even though it's technically following the same rules. So large sample size, all expected counts. And like I said, I'm going kind of quick through this because I'm going to slow down as I need to. Are greater than or equal to 5 because we're going to have so many that we're not going to make sure all of them are at least 10. We're going to make sure all of them are at least 5. And then independent, what do we always check for independent? And again, this is one of those where I kind of say, there are ways to get around independent the way we do it. It's easier to stay consistent and then not have to worry about those ways in between. But I'm saying that because since we're doing a chi-square test of independence to see if they're independent, I can see how that's confusing that we are checking off in the middle that it is independent. But that's kind of one of those that I do without having to deal with too much. And random, we're checking random selection, random assignment. Most of the time we're going to be dealing with random selection for these though. Our test statistic is going to be doing a chi-square. So instead of having like, this is our test statistic. Usually we write test statistic equals. It's just going to be, instead of a t or a z, it's a chi-square. And our equation for this is the sum of the observed minus expected squared divided by expected. That's actually one of the equations you get on your equation sheet for the exam. With a test statistic, if it is a t, what do we also need to know? Degrees of freedom. So we also have degrees of freedom with chi-squared. This is a very generic way of explaining it, but it kind of is pretty much as correct as you need to know for this class. If we are dealing with, one variable, that means there is one parameter that is estimated. So with t, how do you find degrees of freedom? N minus 1. Well, now we have a variable for our columns. We have a variable for our rows. So we basically do n minus 1 with each one of them. So we have number of rows minus 1 times number of columns minus 1. To get our degrees of freedom because we're dealing with two variables now. And then the rest of the notes are an example problem. I'm going to go through how to do like the charts of using the example problem. We're going to switch back to go to 4-step process generic, and then come back to kind of tying it all together at the end. So we're just going to basically talk about, for the rest of this, we're going to talk about this part right now. I'm getting to that part right now. So it's going to give you the first chart. So in this one, we have two different categories. The study of heart disease in male federal employees, researchers classified 356 volunteer subjects according to their socioeconomic status and their smoking habits. Here's a two-way table that summarizes that data. So what is that variable called? Like, what is the generic term that they gave? High, middle, and low, or what? So that's technically our column variable, which, like I said, I don't care which ones are column, which ones are row, because you could technically run either way. Our other variable is what? So the two things we're going to be filling in eventually as our null hypothesis would be that socioeconomic status and smoking habits what? Are independent, and then we would fill it in the same thing for our alternative. So the first thing we need to do here is find our totals. What does it mean to do totals? Just add them. You two do high total, you back there do middle total, you guys do low total. Your group do current total, former total, and then this group right here do never total. Because surely we can just add things up. So you're either adding across or adding down. All right, what's my high total? So we got 211 here, y'all just filling in with me. Middle total would be my low total. And then switching over here would be my current total. My former total. Never total.
99.
And then, so how do I find what goes here? So either add this way or add this way. I always do both to make sure I didn't mess up somewhere. But you should end up getting 356. So this chart right here is something that would be given in the problem. The only thing we had to do is figure out the totals. So we haven't really done anything yet. That's essentially all given. So that's the actual or the observed. You might want to write on your notes somewhere that this is the observed. Because of the way we do our equation, it says observed minus expected. So all those are our observed numbers. So we've got to figure out our expected. So the expected count is how many we would expect. So here I want to know how many current high I should expect, how many former high I should expect, and everything based off of what we have. So in order to do this, we take our row total times our column total and divide it by the overall total or the table total. And that'll give us how many we expect of each category, each pair of categories, I guess, there to be. So because this is notes, I'm going to start out by writing what I multiplied to get there, but eventually you'll just need to write the answer. So what is if I'm trying to find this one for high intersecting with current, what is my row total there? So are my rows socioeconomic status or smoking habits? Rows are this way. Smoking habits. So what's my total for current? So I'm taking 116 times what? Times 211 and dividing that by 356. And like I said, I'm only writing that because it's notes. I don't expect you on a test to write out all that. But let's write out at least a couple of them. So high and former, what would I multiply? What's my row total? High former, what's my row total? 141 times divided by, and just so that you have stuff to look at, let's do this very, very last one down here, never and low. What's my row total for never and low? 99 times, and then divide that by, and then so I could write all these out, but I don't need to, yeah. So doing the math, and then we'll write it all in. Some of y'all started, I don't care. You guys do high and middle current. You guys do high and middle former. You guys do low, former, and current. You guys do high and middle never. And you guys do middle and low never. And then we'll have covered everything. And you're just multiplying so we can not see her multiply all day. Say it again. Did I even tell you? I have probably not. Just multiply a couple and make sure you get them right.
I know that.
Yeah. Let's go to 4 because we're usually good about going to 4 with stuff like this. I typically go to 4 with these. Sometimes it'll be high numbers and sometimes it'll be really low numbers. What did I get for high current?
58.75.
What's the other one I made you do?
It was low current,
Okay.
and that's 16.94 for me.
Alright, let's skip to y'all that did former high is what? And former middle? And then I had a group do current low. What'd you get for current low?
30.34.
And former low?
36.834.
I know I kind of mixed these up. Somebody tell me what high never is.
58.6769.
Does it end up rounding to 770?
Yeah.
Okay, I have that one, 770. Okay, and then middle never?
14.0607.
And then somebody give me my last one. I don't have that written down for some reason.
25.264.
3624.
8624. 8624.
Alright, so my biggest thing is, there's a reason I'm going through these kind of quick and making y'all only do a couple, which I'll show you in a second. You need to know how to come up with these, and sometimes a problem on the AP exam is going to be like, how many should you expect to get for former high? You understand the process of how to get that exact number now. Alright, so we've got our expected, we've got our observed. which means we now have a third table of finding our actual chi-square values. So we have an equation for chi-square values, which is observed minus expected squared divided by expected. So these are our observed that were given. These are now our expected. Let's go ahead and do the same ones you did for finding the expected. Go ahead and find those for chi-squared. And I just showed it with one cell, so that I would write at least one out, so that if you go back and look at it later, you can remember how you got that number. What I get for current high. And your decimals is going to change with, like, some people's decimals might be off by a little bit. Mine was off a little bit there because of there's a reason I'll explain later. Middle current, right? What's that one? Yeah, I think you just typed it out. What's former high? Former middle? While I'm talking right here, this is a very small number, and this is a bigger number. Why is this a small number? Based on, so let's look at, so I'm looking at middle former. My middle former expected was 20.5955. My observed was 21. Why do I get a really small number right here? Because those are really close. What I expected was really close to what I actually got. So I'm going to tie that back in a second. Okay, we ended up getting to that one. Yeah. All right, low current. 5.3197. Former current, or former low, sorry.
2.118.
High never.
1.4.
Middle never.
97.
Something you type something wrong.
I think 2.06.
Yes. 2.06 what?
21.
And then low never.
0.5768.
And again, just like before, something on the AP exam could be how much did middle never contribute to the chi-square statistic? Another very common question that would come up, and people, it's so easy, but people forget about this one, is what contributed most to the chi-square statistic? So what do you think contributed the most to the chi-square statistic? Low current. Which one is the highest of those numbers? Low current. So that contributed most to the chi-square statistic. What does it mean that it contributed the most to the chi-square statistic based off of what we were talking about with middle former being so low? The observed was really different from what we were expecting. So in order to actually come up with, these are all pieces of the chi-square statistic. You don't need to write anything with this right here. I would write this showing where you got one of these, if you haven't yet, because I know you are doing math faults on that. Our equation for chi-square is sum of the observed minus expected squared divided by expected. So these are all pieces. What do I need to do with all these pieces to actually get the chi-square value? Add them all up, which we're going to do in a second. So let's switch gears and go to our generic. So this is the